Welcome to Wednesday. And we're moving on to infinite series and how we can come up with a sum for those infinite series. So we're halfway there. It's almost the weekend, and it's a 3-day weekend at that. We got a nice Memorial Day coming up. So what I'm referring to as far as what an infinite series is back to our vocab words from before, is where we talked about a finite series first, which just means that there are a countable number of elements that makes up the series. So like there's 5 or 6 terms and then you add them up. We talked about the formulas for both an arithmetic and a geometric series that has a finite number of terms. But now what about infinite series? Is there actually a way that we can come up with a way to add them all up? So just to start off with, I'm just going to do a quick little view here of what I'm talking about with a diagram. So an infinite series, as you can see in the circle to the right, it would end up being this series. And you can see each one of those terms represented by the same slice of the circle in our little diagram. And you can see also that this is a geometric series because we multiply a certain value to get the next one, and that makes that common ratio to be a half. Again, you can see each term times a half gets the next one. And so again, we can do that, and you can see I start with one whole circle, and then I have half of the circle. And you can see that that's here in blue, and then I add in a quarter of the circle, then I add in an eighth, and then I add in a 16th. And do we actually come up with a value, even if we keep going forever, that all of these terms would equal? Is there a certain value that all these terms would equal? Even though there's an infinite number of them, is there one specific value that they could equal? Let's explore how we go about figuring this out. So let's look at the series that we were just talking about, 1/2, 1/4, 1/8, 1/16. And as I said, it's a geometric infinite series with the common ratio being 1/2. Don't forget to print off your notes from classroom so you can follow along. So with a common ratio of a half, you can see that each one of these terms are created by multiplying by a half. And you might think maybe it is impossible. How do I get one number as an answer if I'm adding up an infinite number of terms? How can we do that? So I'm going to use a square now. It doesn't matter. We could actually use the circle or the square, but I'm going to show you the square also that that we can use in order to come up with what is the actual value. Is there actually a value that I can add for an infinite number of terms? So let's just take a look at the circle itself, or excuse me, in this time the square itself, and I'm going to draw the square. All right, so there's my square. And to begin with, again, I'm saying, all right, let's add up all the pieces. I'm going to represent a part of the square with each term and see, is there actually some value or some part of the square that I get from adding these together? And you can see this is the overall aspect of it over here on the left-hand side, but you might see it a little bit better as I draw it and go along. So here is half of the circle. There's my half of the circle. And then I'm going to add a quarter of the square. I never really start to cough until I start to make videos. And there is a quarter. So now I've added a half, and then I added a quarter of the square. So now you can see we actually have 3/4. Is that my answer? Well, an eighth, which is, again, if I take half of a quarter as an eighth. So if I add that to this part, we're going to get a little bit bigger. And you can see now that we go from having 3/4 of the circle to having 7/8, just 3/4 plus an eighth. And then if we again add a 16th, which is half of this, you can see that we get this. Now we can keep going on and keep adding half of whatever we have. What do you think is going to eventually happen as we keep adding a half and a half and a half of what we have left? Because that's what we're doing with our geometric series, where our common ratio is a half. What do you think we'd end up with? Are we going to end up with more than the square? If you kind of focus and just keep taking half of a half of a half of whatever is left and adding it and adding it and adding it, well, you actually will just end up with the whole square itself, as we have an infinite number of terms and continually taking a half of each of whatever we have left. So as far as what that would look like in sigma notation for this infinite series, we have our sigma, we have n equals 1, so that's what our first term would start with, as n as being 1, and since it's an infinite series, we're going to go to infinity. So if we plugged in 1 into our formula here, 1 over 2 to the first power, right, that's 2. 1 over 2 squared, that's where the 4 comes from. 1 over 2 cubed, that's where 8. And again, we could keep going on forever. And if we did add them, as I just showed you with a nice little diagram, this actually ends up being 1. Even though there's an infinite number of terms, it's 1. Why does that happen? How can it just end up being equivalent or equal to 1? What happens to each of these values as you multiply each by a half? What happens to the terms themselves? Think about that. So here's another example. And now here's our series: 1/4 plus 1/16 plus 1/64 plus 1 over 256, etc. Well, let's start off and think of first what kind of series this is, which should always be your first question, so you know about how to answer. So this series is a geometric series because we multiply each term by a quarter to get to the next one, and so forth and so on. So again, I have a diagram that's done, but I will draw and see if you can follow along as we go to see, well, what does this add up to, if to anything? Is it like the last one and we end up getting 1 for a sum? So my first term is a quarter, so I'm going to add up each one of these terms by taking each parts of those squares and adding to see what we get. So there, I divided the square up into fourths. So now a fourth of the square is this over here. Okay, so there's a fourth, but now I'm going to add in a 16th. And a 16th is 1/4, is a fourth of a fourth. So here's my 1/4, and if I take 1/4 of a fourth, which is what I just did, I divided it into fours, and then I add a 16th, which would be one of those blocks. That's what I get. And then if we keep repeating that process, dividing one of the 4 blocks into fours, and then taking one of them and then adding them up and keep going and going and going, what would we end up with? Well, as what you can see over here in the left side, trying to get my mouse to find out where it is, which I don't know where it went. But if you look over here on the left-hand side, of the 3 sections that are in red, you can see that each time when we take a quarter of them, only the number 2 slot, well, only the number 2 slot gets filled up. That's it. Okay? Only the number 2 of the 1, 2, 3. 1, 2, 3, 1, 2, 3. Of those, only the number 2 spot is where I'm adding the part of the square that represents the term. So what do you think this is going to add up to? Or does it add up to anything if I keep taking only this spot right here as we do this continual process? Is there a value? What do you think it's going to be? Well, again, if you take a look at it, and you'll see that it's only one of the 3 spots, and in repetition as we add, that is 1/3 of those 3 spots that always gets added that represents the terms. So of the 3 spaces, only the number 2 gets filled up. So therefore, this is actually going to add up to 1/3. Again, that's just a visual. Is there like a more mathematical way to go about doing this? Of course there is. And that is using what we call the partial sums. Remember, a partial sum is adding up a specific number of terms of a sequence. So this is an infinite series where, again, we have the terms that we just talked about from above. So if we, again, focus on the partial sums to see, do we actually get a third? I'm going to start by taking a partial sum of, just to do S1, then S2, then S3, then S4. So this is my first partial sum. This is my second partial sum, my third partial sum, my fourth one, etc. So what are they equal to? What are those partial sums? So obviously the first partial sum is just going to be a quarter because it's just 1/4. But now I'm going to take a look at the second partial sum and see what that is. Well, you could get common denominators, which this would make this 4/16. So that would be 5/16 is what this partial sum is, which as a decimal is 0.3125. So once again, we said up above that our series added up to a third. And remember, a third is 0.3 repeating. So that's what I'm trying to check out. So if I take another partial sum, which now is our third partial sum, and you can check this on your calculator. Again, if you wanted to do this by hand, more than welcome to do so. Get common denominators, add them all up. But this is your decimal representation as you added those all up. And then our fourth partial sum, 0.32320. And hopefully you can see that as we're doing these partial sums, we're actually getting closer and closer to this value of 0.3 repeating. And if you wanted to, you could find the next term and add them all up and see what you got. And see that you're getting closer to it. You'll never go over it. You'll never get bigger than that value. But you're actually approaching this number of value of a third. So partial sums actually help us out. And what that means is, as far as taking our partial sums, we need to let n approach infinity and keep taking them over and over and over again to see what value that's approaching in order to calculate our infinite series values, if there is indeed one. And I hope you're probably saying, do I have to do that all the time? Taking all these parts, take a partial sum, take another one, take another one. Yeah, that would get kind of monotonous. So we have to have a better way for that. So talking a little bit further about it, how are we going to explore doing that? So we're going to introduce some vocabulary words, and the first one is converge, or to be convergent. And this again is our infinite sequence, our series that we've talked about before, infinite series. So if we add them up and then we take a look at the sum so far, and remember the sum so far, as you see down the bottom, the sum so far are our partial sums. And if it actually approaches a finite value, we say that the series is convergent. Remember, just like a word in any other context, when you converge on something, it means to come together. So convergent for a series means it comes to a specific value, a finite value. So again, if we take a look at this, here's our infinite series, and this time our R value is a half. Again, we've looked at this before. And do you remember what the sum was? Right, what we said it was? We actually said the sum for this was 1. So let's take a look at the partial sums, because we haven't done that for this type of example. So our first partial sum is a half, and then we're going to add a quarter. It's not just a quarter, but we're going to add a quarter and a half. So when we do that, we get 0.75. And again, I did mention that with a square. Then I'm going to add an eighth to 0.75, and we get 0.875. Now we're going to add a 16th, and we get 0.9375. Then I'm going to add a 32nd, and I get 0.96875. So I hope that you can see, and if you really don't at the moment, you can keep adding some more. Add in a 64th, add in 1 over 128. Keep doing that. You'll see that the sums are heading towards 1. So this series, therefore, is what we call convergent. It is convergent towards one or has a finite limit is another way that we can say that. And if you think about our rational functions, when we came up with our horizontal asymptotes, these limits had a lot to do with how we actually place them. We didn't refer to them using the concept of limits, but we actually thought about them more generally in the number sense. But this series, again, when it converges towards a specific value, a finite value, we call it convergent. And you probably could come up with, well, what if it doesn't approach a finite series or a finite value? Well, that's divergent. So if the sums do not converge, then it is diverge or divergent. And therefore, what that means is that the sum will either go to positive infinity, or it will go to negative infinity, or it will just go up and down without settling on any value. So for example, what kind of series is this? Right? Is it arithmetic or geometric? Those are the only two we talked about. And remember, arithmetic is just when you add the same value to get the next one. Geometric is when you multiply the same value to get the next term. So as you look at this one, I hope that you can see that this is an arithmetic series with the common difference being 1. So what happens to each one of these terms as you keep going on? And remember to keep that in mind when you're adding them up. Is it actually going to approach some specific value? So our process is still the same thing, where we're going to look at our sums so far. So obviously, my first sum would be just 1 by itself. Now I'm going to add the first two terms. So our second partial sum is 3. Our third partial sum is 6. And then you can see we can keep going and going. We get 10, then we get 15. And hopefully you'll see also that it says the sums are just getting larger and larger. They're not heading to any finite value, because if you look at the terms themselves, they are also just getting larger and larger. I got 6, then I'm going to add 7, then I'm going to add 8. So in this case, this arithmetic series would just head towards infinity. That's what it would add up to, and therefore we would say that it's divergent. And then the example of it where it says going up and down without settling on any value, where it also referred to as being divergent, is a series that looks like this. And this is a geometric. It's just when we multiply by -1 to get the next term. So we got a geometric here with the common ratio being equal to -1. So you can see that the numbers themselves goes from 1 to -1. And then if you added them, 1 minus 1, right? Well, first partial sum is 1. Second partial sum, 0. And as sum, even though it says a minus, 1 plus -1, that's 0. And then the third partial sum, we'd be back to 1. And the fourth partial sum, we're at 0 again. And that would going up and down from 1 to 0, 1 to 0. So there isn't one specific value that this would head towards. So therefore, again, it's divergent. There isn't an answer for it. It's not infinity. It's not negative infinity. It's not 1. It's not 0. We just say it's divergent and there is no sum. So how are we going to decide on which ones actually come up that we can come up with an answer for, and which ones we just don't know, or we can't figure out a value for? This is not in your notes, so you can just write this below that page that you just ended off of. But I did want to add in some examples so you could come up with your own thoughts on this before I actually just tell you what it is. How do we decide? How to decide which infinite series converges and which ones diverge? So I have a few examples that are here. And here's another one down there. So we got 5 different types of series. So what I recommend, as you should always do for anything, is to first figure out which type of series are we dealing with. So up here, if you look, you're probably getting better at this. We can see that this is a geometric series with r being 1/2. How about the next one? You got that? What do you think the next kind of series is? We have -1/4, then a +16th, then a -1/64th, then a +1/256, and then this is a negative. So we're going back and forth, but it still is a geometric because we are multiplying, and in this case, because it goes back and forth, alternating, and that would help me determine that it's going to be a negative. -1/4 is that common ratio. And then if I look at the next one, we actually just talked about this one. That's an arithmetic series uh, with a common difference of 1. And then if we look at the next one, is that geometric or arithmetic? That one is also arithmetic, and that's with a d being -4. Again, you add -4 to get the next one. Or again, if you aren't sure for both geometric and arithmetic, you can take a term and subtract or divide and find out what that difference is without actually having to calculate it yourself, because that actually is easier. If you take this term and go back, 2 minus 1 is what? 3 minus 2 is what? That's where we get our common difference, is by actually looking backwards. So D is 1 for this one. Up here, 6 minus 10 is what? 2 minus 6, -2 minus 2. All of those, again, have a common difference of -4. And up here, if you do it with your geometric, 1/16 divided by a -4. And, excuse me, you can see, again, how we can come up with those common ratios. All the way down to the last one, what kind of series do we have here? 2 plus 4 plus 8 plus 16. Is that arithmetic or is it geometric? So once again, I think it's either division or subtraction that I'm thinking, and that will tell me if it's arithmetic or geometric. So 4 minus 2 is 2. Is that a common difference between 8 and 4? No, that difference is 4 for 8 and 4, and the common difference, or at least difference between 16 and 8, is 8. So there is no common difference. So that means it would have to be a geometric if it is arithmetic or geometric at all. So if we do a common ratio, 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2. So that means it's a geometric series because we have a common ratio. Now, as far as looking at each one of these and once again trying to decide, well, how do I know if I can figure out, because these are infinite series, they're going to go on and on, for the information that I have, can I actually calculate a value? Well, what I want you to take a look at is the terms themselves again. What happens to the terms themselves as you continue to make the series? And then based on those terms, will it actually add up, be able to add up to something? So what I want you to do for the arithmetic ones, all right, we're going to take a look at those first. And you'll see that, right, those right there. I gave you both examples of a positive common difference and a negative common difference. What happens to those terms as you either add or add a positive or a negative? And really, any number that's either positive or negative. What's going to happen to the terms themselves? So when I add a positive whatever to each one of the terms are going to get bigger and bigger and bigger, and they're just going to keep getting larger and larger. If I add a negative number to whatever number you decide to start at, and you keep doing that for an infinite number of times, what's going to happen? Well, those numbers are going to get really small negative. So we can say that they're a big negative number. So for an arithmetic series, are they going to actually be able to approach a specific value if the terms themselves get larger and larger? Right? Each one of those terms, they get larger and larger and larger, whether it's positive or negative. So big positive or a big negative numbers. If you keep adding them up, no, it's not. if we add these, they're going to end up being positive infinity. And if we add all those up, that's just going to end up being negative infinity. So for the sum of an infinite arithmetic series, you're never going to be able to find it. These are always divergent. So an arithmetic is always divergent because the terms themselves, keep getting either big positive or very big negative. So therefore, if you added them all up, they would either go towards positive infinity or negative infinity. So we can't end up with an answer for that. Now let's take a look at the geometric ones. What happens with those terms if we take a look at those? So for this first one up here, what happens to the terms themselves? So I got a half, which is 0.5. Put that in there. And then this is 0.25. That's 0.125. If you keep going, you can see for this geometric series, the terms themselves actually are getting smaller and smaller. Does that happen for the next one as well? So I got a negative 0.25 and then 1/16, which don't know that one off the top of my head. That's a 0.0625. And then 1 divided by 64, that's going to be a negative 0.015625. So even though they are either positive or negative, these numbers are getting smaller and smaller. Okay? So they're getting smaller, smaller, smaller. Each one of them, they're getting tinier and tinier. So those are these two geometrics up here. Again, whether it's positive or negative for a common ratio, the numbers themselves are getting smaller. How about this geometric series all the way down on the bottom where the common ratio is 2? What happens to the terms themselves? The terms themselves, 2, 4, 8, 16, then if we kept going, 32, 64, they'd, excuse me, keep getting larger and larger themselves, just like those. They get larger and larger. So if the terms are getting larger and larger and we're adding them all up, just like the arithmetic one, this geometric series would approach positive infinity. So there isn't a specific number. Are we able to again figure out how can I decide what types of series can we figure out, infinite series can we figure out actually have a value that we can find when we add them all up? So let's see again what we've talked about so far. We have our arithmetic series. Regardless of our common difference of either being positive or negative, it's always divergent because the numbers either get really big positive or really small negative. So that's not going to work. We can't find numbers. So arithmetic series, always divergent. Don't forget that. Now, geometric. We've taken a look at two different kinds of geometric series where the terms themselves gets bigger and bigger and bigger. So this would be divergent because it does not approach a finite value. And if you think about if the common ratio was like -4, right? If we start at, let's say, 5 and the common ratio is -4, then this would be -20. And then -4 times that, I'd get a positive 80. And then -4, that'd be -320, dot, dot, dot. What's going to happen to those? Is that going to actually converge to anything? Well, the numbers, again, regardless whether they're positive or negative, they're getting very large again, too. If they're not getting smaller, they're getting larger. So even if the common ratio is negative, it's not going to approach a specific value because those numbers are going to get really, really, really big. So geometric series, where the terms are getting larger and larger themselves, we can't figure out a value for. Go back to the ones that are up here. Once again, if we look at those, the terms are getting smaller and smaller. What's eventually going to happen to those terms? They're going to get so small, they're going to be almost what value? If we keep following this geometric progression and come up with our series, these numbers will be eventually so small, they're going to be very, very close to be equaling what number? Another cough. I'll get a drink while you think about that. As they get smaller and smaller, what number do they eventually going to be close to? They're going to eventually be closer to 0. So therefore, if you eventually add numbers that are so close to being 0 that all those numbers would have added up by then to some finite value. So these types of geometric series are the only ones that can be convergent. And what can we conclude that is? Well, the conclusion is that the only types of convergent series, see if I can move everything out of the way. Okay. So a convergent series are geometric because, again, with arithmetic, the terms just keep getting either larger positive or very large negative, so they wouldn't add up to anything. So convergent series are geometric, but I showed you above that not all geometric series are convergent, because if the R value was 2 here, then the numbers kept getting bigger and bigger. So that was divergent. But these ones, the numbers actually got smaller and smaller, so therefore they would actually go towards a specific finite value. So it's all about that R value, because if R is bigger than 1 or equal to 1, those numbers either aren't going to change. Like if R was 1, the numbers wouldn't change, and I would just be doing 2 plus 2 plus 2 plus 2 plus 2 plus 2, and that would be, again, going towards infinity. So if the R value is 1 or bigger, the numbers themselves are going to continually get larger. And then if we added all those numbers up that got increasingly larger, it would go towards infinity. And if the R value was -1 or smaller, again, those numbers would be getting still larger, or either being the same value over and over again, or repetitive, I'm sorry, if they were negative. And again, they wouldn't add up to anything. So it's all about that R value, and that R value must be in between -1 and 1. And this is the important thing for our convergent series, right? That it has to be geometric, and the R value has to be in between -1 and 1, which once again, it means it's a fraction that's smaller than 1. So you're multiplying it by a smaller portion of itself, therefore making it smaller, and eventually being able to add up to some finite number. And if it's equal to 1 or bigger, those terms are going to get larger themselves and then just add up to infinity. So, is there a formula for it? Can we actually calculate that without having to do all those partial sums like we talked about before? Well, we probably then should just start off the formula for any geometric series for the first n terms, right? This was our formula from before. So we're going to delve in on what this means now, because in the finite geometric series, we knew what n was, we'd know what r was, and we'd know the first term. So we could just plug in those numbers and get an answer. But now when we're talking about an infinite series, this means that n is going to be approaching infinity. So that means that this n value right here is going to be very, very large. It's going to be infinity itself. So what actually happens to the common ratio when we raise it to a very, very large power? So let's examine the infinite series with r equal to a half. What happens as r to the n increases? And as far as being able to come up with this formula, why we chose r equal to a half. Remember, we just said the only ones that we can find a value for are the ones with a common ratio in between -1 and 1. So I don't want to look at this formula with something that's not in this range, or it's just going to be infinity anyway. So that's why we're looking at a value in between -1 and 1. So let's square a half, then cube it, then raise it to a fourth and see what happens. So we got a fourth when we square a half, because right now we're just taking a look at r to the n and see what happens as n gets very big or approaches infinity. So as we keep raising 1/2 to a larger and larger power, right? As n gets very large, what happens to r to the power of n? Well, it's going to get very small, right? Because the next one is 1/32, then 1/64. I didn't write that correctly. Then 1/64th, then 1/128, and going and going and going and going. So therefore, it's getting very small. So therefore, we say that as n increases without bound, a bound is just, okay, stop here, but it has no bound. So n is going to keep getting bigger and bigger and bigger. So r to the power of n is going to approach 0. And therefore, our formula, if we look right here, we just said that term, that r to the n, is going to be 0. So that part that's in the parentheses, that 1 minus r to the n, well, what's that going to approach then? Well, if r to the n is 0, 1 minus 0 is 1. So this makes the numerator then approach what value? So if, again, you take a look at our sum and look at what we just said, we had a to the 1, 1 minus r to the n over 1 minus r. That was our formula. And we just said that this part right here, r to the n, is going to be approaching 0 as n gets extremely large. Right? This is what we're looking at right now, because we're trying to find the sum of an infinite number of terms. So if n is large, again, this ends up being 0, so that goes away. 1 minus 0 is just 1. And then what happens to the top? Well, a sub 1, the first term times 1 is just going to be the first term. So therefore, we got our formula. The sum of an infinite series is what you see here. A1, your first term, divided by 1 minus the ratio, or the common ratio of that. And I put that a little bit more definitively in this next slide. So again, you need to make sure that you know what that is. But in order to do that, you need to go through a couple of steps. Given an infinite geometric series, find its sum. Well, first thing you have to do is to obviously know the first term and the common ratio. And you got to make sure that that common ratio is in between -1 and 1. And if it's not, then you can't add it up. It has to be in between there. Because remember, if the common ratio is larger than 1, you'll get larger and larger terms. And therefore, if you try to add up terms that are continually getting larger, they'll just approach infinity. So we have to have values or terms that are increasingly getting smaller or approaching 0. So then we can eventually find S, which is that infinite series answer, or the sum for that infinite series. So before I let you go and I give you your assignment, just a quick couple of examples that you have here. So what we're going to do is determine whether the infinite geometric series is convergent or divergent. And if it is convergent, find its sum. So right off the bat, if it is divergent, you are automatically saying that it has no sum. So that's why you don't have to say it's positive infinity or negative infinity, which you could, because it could be either. Or you could just say it has no sum because it could waver in between like 1 and 0, like an example we did before. But for this example, it's just either convergent or divergent. And then we're going to find that sum using the formula. So as we said before, the first thing that you need to do is first make sure you know it's a geometric series. And that would entail figuring out what's r. So if you look at this, you'll see that I have 2, then I have 2/5, then 2/25, then 2/125. Well, that makes our 1/5. And if you weren't sure of that, again, remember you can always go backwards. 2/5 divided by 2. 2/25 divided by 2/5. And you can find that common ratio. So we needed to know r, which it's 1/5, and therefore, because it is in between -1 and 1, it does have a sum. So this is convergent. So to find its sum, we need the first term, which is 2, the common ratio, which is 1/5, and plug them in. So we would end up with s equals 2 over 4/5. And remember, you do skip, change, flip. So that is 2 times 5/4, which is 10/4, which is 2.5. Oh, how did that turn into an eraser? So we get 2.5. So that's the sum of that infinite series, 2.5. Right. If you want, you can, again, pause it and do these next two to see if you can do them on your own. So again, if it's going to be either convergent or a divergent, it has to be a geometric series with a common ratio in between -1 and 1. So you need to first check, is it a geometric series? Which once again means, am I multiplying something to get the next term? So 1 times what is 7/5? Well, that one's pretty easy, right? It'd have to be 7/5. 7/5 times 7/5, yep, that's 49/25, and then 7/5 times this, we get that answer. So r is 7/5. So it is indeed a geometric series, but remember, it has to be in between -1 and 1. And r is actually 1.4, right? 7/5 is 1 and 2/5, or 1.4. So therefore, it's divergent. Because again, if you keep going, these numbers, even though you're seeing them as fractions, are actually getting bigger and bigger and bigger because you're multiplying it by something larger than 1. So those terms are getting bigger and bigger and bigger. And if you really needed to, you could say they're divergent and they're going to head towards positive infinity. Now, the last one, decimals. How do we figure that one out again? Is it a convergent or is it going to be convergent? Well, first, is it geometric series? So again, 99.4 divided by 248.6. And then that should be the same thing as 39.776 divided by 99.4. This is 0.44. This is going to help you figure out what your common ratio is. So use your calculator to do that, and that ends up being, yeah, they actually are the same. They're 0.4. So because it is geometric and our R values in between -1 and 1, it is convergent. And now we just need to figure out, okay, that means that these numbers are getting smaller and smaller. So if you actually take a look, you can see that. We've got a 248 to 99 to 39. And now that we see the common ratio, it's smaller than 1. So we're multiplying the numbers by something smaller than 1. So the numbers will get smaller. So our sum is going to be our first term on top, 248.6. And then we have 1 minus the common ratio, which is 1 minus 0.4. So plugging that into your calculator, we get 414.3 repeating. So that is our notes for today. I hope that you found these interesting and hopefully easy as you followed along with our exploration into figuring out which types of series were convergent or divergent and how we go about doing that. I think it definitely makes a lot of sense. And you're like, oh yeah, I get that. I see how it works. If you're still not sure, as usual, send me a remind text or whatever, and I can answer your questions. But to finish off for today, got our assignment, and that's going to be on page 938, 16, 24, 33, 34, 35, and 37. And this is due Thursday night, which is tomorrow. Every day seems like the same day. I always have to figure out what day it is, which as of right now, I don't know what the date is. So today's the 20th, so that means tomorrow's the 21st, and at midnight. So continue to keep working, and again, send me any texts, any questions that you may have about this. And there are a couple more pages that you'll see that were in the print-offs, but that is where we're headed next. So don't throw them away if you printed them all out, like I hope that you had done, so you could follow along and make your own notes. And we're all done for today. Make sure you write your assignment down. Again, get some practice in, and get out and enjoy some sunshine.